Hello, this is Yashveen. In this video, I'll be solving paper 2 variant 3, May-June 2021 9701 chemistry. 1. The elements in group 17 are known as halogens. A. Between the molecules of group 17 elements, van der Waals forces exist. 1. State the trend in the relative strength of the van der Waals forces going down group 17. So these are the forces that exist between the molecules that hold them together and give them their physical state, and they occur due to the electron cloud of an atom of an element. And going down group 17, or any group for that matter, the number of electrons increases, which means the strength of van der Waals forces is going to increase. 2. State the physical state of each of the halogens under room conditions. So chlorine is going to be gaseous, bromine is liquid, and iodine is solid in state. B. A solution of aqueous bromide ions is added to separate samples of chlorine, aqueous chlorine, and aqueous iodine. Describe what is observed in each reaction. Explain your answers in terms of the relative reactivity of these elements and oxidizing agents. Alright, so chlorine over here is a stronger oxidizing agent than bromine, meaning that it has a greater magnitude of attraction for electrons, so it's going to oxidize bromide ions and gain those electrons to become chloride ions itself, which is why when added to bromide ions, chlorine will turn the solution into orange brown color, which is essentially due to the fact that you've got bromine atoms now instead of bromide ions that cause the color change. And then with iodine, bromine is a stronger oxidizing agent than iodine, which is why no reaction occurs between bromide ions and iodine. So bromine has a greater attraction for electrons than iodine does. Now this happens because of the fact that you know that going down the group, the atomic size of halogens increases, which means that the shielding effect of the outer shell electrons also increases. As you go down the group, the nuclear attraction for outer shell's electrons decreases, which also means that the attraction for electrons that could have been added to the last shell also decreases, which is why going down the group from chlorine to bromine to iodine, the attraction for extra electrons decreases, and therefore their strength as oxidizing agents decreases. C. Bleach is made by reacting chlorine with cold sodium hydroxide. Write an equation for the reaction of chlorine with sodium hydroxide. This is a reciprocation reaction where chlorine reacts with sodium hydroxide, and the oxidation state of chlorine changes from 0 to +1 and -1. And this is how the reaction goes. You've got sodium chloride, so over here the oxidation state of chlorine is -1 and it's 0 in its molecular form. And then you've got sodium chlorate as well as a water molecule. So to balance out the two sodium and chlorines on the product side, I'll write down a 2 on the reactant side as well. D. When aqueous chlorate is added to water, it behaves as a Bronsted-Lowry base. Define the term Bronsted-Lowry base. So these are species that accept hydrogen ions or protons. 2. Write an ionic equation for the reaction between chlorate and water. Alright, so we know that chlorate is going to act as a base. So it's going to accept a hydrogen ions, which means it's going to form the hydrogen chlorate compound. And so the negative charge of the chloride ion disappears in the product, and this hydrogen ion had to have come from the water molecule, which is why you're now left with hydroxide ion instead of water molecule. E. The concentration of sodium chlorate in bleach S is x gram per dm cube. Sodium chlorate reacts with hydrogen peroxide as shown. So you've got sodium chlorate reacting with hydrogen peroxide, and this forms water, sodium chloride, as well as oxygen. A 5 centimeter cube sample of S, so the bleach sample, completely reacts with hydrogen peroxide. The volume of oxygen produced is 24 cm cube under room conditions. Assume that only the sodium chlorate in S reacts with hydrogen peroxide. Calculate X, and you're supposed to show your working. Alright, So here we've got the concentration of sodium chlorate as well as its volume. And then we've also got the volume of a gas, oxygen gas. Now we can use the volume of gas to calculate its number of moles. However, the volume and the concentration, we don't have the complete concentration of sodium chlorate, which is why we cannot use the formula to find out its moles. So let's start by finding out the number of moles of oxygen. That means that would be equal to volume divided by molar volume, and we'll need to convert 24 cm cube to dm cube, which is why you will divide that by 1000, and then the value that you get would be the value in dm cube, and you divide that by 24, the molecular volume, and the answer for that is equal to 1 times 10 to the power of -3 moles. Since we're using the formula, moles of a gas is equal to its volume divided by molecular volume. Now we did that because we need to use somehow we need to use the information that were given in the question, and now we can convert this gram per dm cube to mole per dm cube, because those are the standard units that we need to work with. So to convert from mass to moles, we know that moles is equal to mass divided by molecular mass, which means that moles is equal to mass divided by molecular mass, and so you divide x by the molecular mass of the compound sodium chlorate, which is 23 plus 35.5 plus 16, which all of these are the masses of the elements present in the compound sodium chlorate, and that is going to be equal to 74.5. So you now have the concentration in mole per dm cube. Now you've got the concentration and you have the volume, so you can now calculate the number of moles of sodium chlorate, which is going to be concentration, meaning x, divided by 74.5 multiplied by the volume. Now you need to convert volume from centimeter cube to dm cube, which is why I divide that by 1000, and this is equal to 5x divided by 74,500. Ratio given in the equation, 1 mole of sodium chlorate produces 1 mole of oxygen gas. That means this number of moles of sodium chlorate is going to produce an exact number of moles of oxygen. Now we don't know the number of moles of sodium chlorate, however we do know the number of moles of oxygen, which is 1 times 10 to the power of -3, which means that we can equate the number of moles of oxygen with the number of moles of sodium chlorate, and using this equation you'd be able to see that x is equal to this value, 1 times 10 to the power of -3 multiplied by 74,500 and divided by 5 is equal to 14.9. This is equal to 14.9 grams per dm cube. F. Sodium chlorate oxidizes dilute hydrochloric acid to form 3 products. The products which contain chlorine have chlorine species with the oxidation number -1 or 0. No other species changes its oxidation number during the reaction. Use the information to complete the ionic equation. Alright, so chlorine having an oxidation state of 0 would mean it's present in its molecular form, so I'd write that down over here. And other than that, we're also going to get a water molecule using the hydrogen and oxygen ions, and there'd be a chloride ion in its ionic form, since we're told that one of the products contains chlorine in this form, and you can balance that number by writing down NH next to HCl, which balances the number of hydrogen as well as the number of chlorines. 2. Methanol is soluble in water because it forms hydrogen bonds with water molecules. Draw a fully labeled diagram to show how a hydrogen bond forms between a water molecule and a methanol molecule. So hydrogen bonds exist in a compound or 2 molecules when hydrogen is covalently bonded to either oxygen, nitrogen or fluorine. In methanol, the hydrogen atom is bonded to oxygen, and so this leads to partial charges, oxygen carrying the partial negative charge due to the fact that it is more electronegative, so it pulls the bonding pair of electrons towards itself more. and so hydrogen is going to have a partial positive charge. The second water molecule, again, it has hydrogen bonded to oxygen, which means that there's going to be partial charge, which leads to hydrogen bonding. So I'm going to draw the water molecule. You've got a partial positive charge on the hydrogen atoms and a partial negative charge on the oxygen. And then you've got the CH3 that is bonded to O and H. Now CH3 has got nothing to do with this. You've got a partial negative charge again on the oxygen, a positive one on the hydrogen, and the bonds formed between opposite partial charges. So hydrogen of the water, oxygen of the methanol, hydrogen of methanol with oxygen of water. B. Methanol has a melting point of minus 97 degrees Celsius and a boiling point of 64 degrees Celsius. A sample of pure liquid methanol is added to a flask and then sealed. The sealed flask is left for several days at constant temperature. The vapor pressure is then measured as 17 kilopascals. 1. Describe what's meant by vapor pressure of methanol. Alright, so you'd get vapor pressure would be experienced when you've got some liquid in a container. Let's suppose it's a beaker, and then you've got it sealed. So you have some liquid. The energetic molecules on the top of the surface are going to evaporate. So they are going to break free of the intermolecular forces, or the forces between that hold the molecules together in this liquid, and they're going to form a vapor. And those exist in the form of vapor over here. Now eventually they'll lose the energy and move back to the liquid form. And this movement exists in an equilibrium, and this vapor in equilibrium with its liquid is called vapor pressure. And in the second part, they'd ask you why some of the liquid becomes vapor. So the answer to that would be the same, that the energetic molecules that exist on the surface of the liquid break free of the intermolecular forces and form vapor. 3. Suggest and explain the vapor pressure of water when the room temperature is lower than the vapor pressure of methanol at room temperature. Refer to the correct intermolecular forces in your answer. So vapor pressure would be low when you've got fewer molecules in the equilibrium, fewer vapor molecules in the equilibrium, which means that when if you had used water instead of methanol in this case, sealed in a container, fewer water molecules would have formed vapor, which means that fewer molecules break off from the surface of the water, meaning that the intermolecular forces between the molecules are too strong for them to be able to break them and form vapor. And so because of the fact that water has stronger intermolecular forces due to hydrogen bonding, and therefore its relatively less number of water molecules are able to escape liquid. C. Methanol is made by reacting carbon monoxide with hydrogen. Carbon monoxide and hydrogen react at 1 times 10 to the power of 7 pascals and 200 degrees Celsius. Eventually, the reaction mixture reaches dynamic equilibrium. The table shows the amounts of each species present in the mixture. 1. Explain what is meant by dynamic equilibrium. So in the dynamic equilibrium, the rates of forward and backward reactions are equal, and you've got this in a closed system. 2. Calculate the partial pressure of methanol at equilibrium under these conditions. Show your working. So the partial pressure of any of the gases involved in the equilibrium could be calculated by dividing the number of molecules of that particular gas by the total number of molecules. So you'd add all of them and then multiplying the answer by the total pressure, which is given in the question as 1 times 10 to the power of 7 pascals. So you've got, and this leads to the answer as 9.2 times 10 to the power of 6 pascals. So my answer here is corrected to 2 significant figures. 3. Write an expression for the equilibrium constant for this reaction and state the units in your answer. Alright, so you divide the partial pressure of product, which is methanol, by the partial pressure of the reactants raised to their concentration. So partial pressure of carbon dioxide multiplied by partial pressure of hydrogen squared, since you've got 2 molecules of hydrogen in the reaction. Now as for the units, you've got a single unit in the numerator divided by pascals cubed, since you had this 2 with the partial pressure of carbon monoxide. And so what you're doing is using the law of indices, you're dividing 1 by 3 or subtracting the powers, which is equal to -2. And so here you've got pascals to the power of -2. Or a better way to see this would be, so you cancel out one of them, and this leaves you with 1 divided by Pascal squared, which is Pascal to the power of -2. Three separate samples of R, S, T, and U are added to cold water. The identity of each sample is unknown. However, each sample is known to be pure and can only be one of barium hydroxide, sodium chloride, phosphorus oxide, or silicon chloride. A1. Use the observations in the table to identify each sample as one of barium hydroxide, sodium chloride, phosphorus oxide, and silicon chloride. So R is a solid. So R can, we know that barium hydroxide and sodium chloride exist in solid form, and it, following addition to water, it forms an alkaline solution which is colorless, and some white solid remains. Phosphorus oxide is also solid. Now between these three solid compounds, sodium chloride will give a neutral solution since it's a neutral compound. Barium hydroxide, on the other hand, provides an alkaline solution, and phosphorus oxide provides an acidic solution. And so out of these three, it's barium hydroxide over here, which is R. And I'd eliminated silicon chloride initially as a choice because it is not solid at room temperature. Moving on to 7, white solid disappears and the solution is neutral. So again, this is going to be sodium chloride because the rest of them do not give neutral solutions in water. T is a liquid which forms misty fumes. Now this is an indication of formation of hydrogen chloride, and white solid is made in vigorous reaction. So when silicon chloride reacts with water, it forms the white solid silicon oxide and hydrogen chloride. So these hydrogen chlorides are represented by the misty fumes, and the white solid here is silicon oxide. So you'd write silicon chloride over here. And then as for the last one remaining, which is a solid, it forms acidic colorless solution in vigorous reaction with water. That would be phosphoric acid produced after the addition of phosphorus oxide with water, after the reaction of phosphorus oxide with water. Identify the formula of the white solid made when sample T reacts with water. So again, this is silicon oxide, as I mentioned earlier. 3. Name the solution formed when U reacts with water. So phosphorus oxide, when it reacts with water, forms phosphoric acid. So I'll write that down over here. B. Magnesium oxide and aluminum oxide have properties typical of ceramic metals. 1. Name one physical property typical of ceramic metals. Oh, they've got very high melting points. 2. Give the formula of another period 3 oxide which behaves as a ceramic material, and you could use silicon oxide as an example over here. C. Tungsten oxide is used to give color to ceramic material. A sample of tungsten oxide contains 79.29 tungsten by mass. Calculate the empirical formula of this oxide and show your working. Alright, so to calculate the empirical formula of a compound, you start by writing down the symbols of the elements and then their percentages by mass. So 72, if you've got out of total 100%, 79.29 as being tungsten, that means the remaining, or 100 minus this percentage, would give the percentage by mass of oxygen. So 100 minus 79.29 is equal to 20.71. Now you've got the percentages by mass and you divide that by their atomic masses. For tungsten it is 183.8 and oxygen's mass is 16, which gives you the answer 1.29 which gives you the answers 0.433 and 1.29. Now to get their ratio, you divide both of the values or all of the values by the smallest number, which is 0.433, which gives the final ratio as 1 is to 3. Now 3 is, which is actually, the value is actually 2.989. And this means the empirical formula is WO3, since you've got 1 atom of tungsten and 3 atoms of oxygen in this compound. For a 1,3-dichloropropane-2 can be made by reacting M. 1 give the systemic name of M. Alright, so in M you've got 1, 2 and 3 carbon atoms in the backbone and chlorine, and you've also got so it's a halogen compound, and you've got a carbonyl carbon and rather a ketone group. So this is a ketone with 2 chlorine atoms. You'd name this 1,3-dichloropropane. To name the functional group present in M that changes during this reaction. So as you can see, the chlorines remain the same. It's the ketone group that changes to the alcohol group. State a suitable reagent for this reaction. So to go from a ketone to an alcohol group, you'd have to use a reducing agent. Here I'd use sodium borohydride. B. Separate samples of 1,3-dichloropropane-2-ol and 3-chloropropane-1,2-diol are heated with excess acidified dichromate ions until there is no further reaction. In each reaction, a different organic product Q or R is made. Alright, so in Q, let's identify the groups that do react with the oxidizing agent, that is dichromate ion. So you've got a secondary alcohol group which will be oxidized to a ketone group. Now in this compound you've got a secondary and a primary alcohol group. The secondary alcohol again will be oxidized to a ketone group, and the primary alcohol group would be oxidized to a carboxylic acid group. And so in Q you've got a ketone group, in R you've got a ketone as well as an acidic group, carboxylic acid group. Q and R are tested separately with 2,4-DN pH and sodium carbonate solution. Complete the table to give any relevant observations. If no reaction occurs, write no visible reaction. So 2,4-DN pH reacts with carbonyl carbons, so that would mean it reacts with ketone groups and an aldehyde group. Since both of the compounds Q and R do have a ketone group, they will react, and this will produce an orange precipitate in both of the reactions. As for sodium carbonate is a base. That means it reacts with an acid. So in Q, you've got no acidic group. It's just chlorine at the terminal carbon atoms, a ketone. And in R, you've got a ketone as well as an acidic group, carboxylic acid group. And so sodium carbonate will react with this acid group to form a salt, which means that you've got no observations with Q, and with R this will produce carbon dioxide, which is why you'd observe effervescence in this reaction. C. Citric acid can be made from M in a 4-step reaction. Complete the table for each step of the reaction sequence to identify the reagents and the conditions required and the type of reaction. Alright, so starting with step 1, let's look out for the changes that are occurring, and to do that I'd like to draw the displayed formula. So you've got chlorine on the first carbon atom, and then on the second carbon you've got the ketone group, third carbon chlorine. This is structure M, and to go from M to the second compound, the change that you'd be able to see is that you're changing the ketone group to an alcohol group as well as a nitrile group. So let me draw the backbone over here. Let me draw the compound over here, CH2, that's bonded to Cl. Again, this is also CH2. Now this carbon atom is bonded to cyanide ion and hydroxide ion. So you're going from a ketone or a carbonyl carbon to this compound, which means this had to have been nucleophilic addition, and to carry out this reaction you'd need sodium cyanide as well as hydrogen cyanide. So sodium cyanide plus dilute hydrogen cyanide. For step 2, again look out for the changes that you are able to see. So the alcohol, chlorine and chlorine remain the same. The nitrile group changes to an acid group. This is hydrolysis reaction, so you need an acid to carry out this reaction. It's in the question they've used sulfuric acid. You could also use dilute hydrochloric acid, and this is hydrolysis. The previous one was nucleophilic addition. And for step 3, again look out for the changes. The acid group remains the same, the hydroxide group remains the same. You're just changing, you're substituting the chlorines. Since chlorine is substituted by cyanide ions, this would be nucleophilic substitution, and to carry out this you'd need sodium cyanide in ethanol, so that hydroxide ions do not act as, because if you had used aqueous sodium cyanide, hydroxide ions could have acted as the nucleophiles, which we do not want. As for the step 4, again look out for the changes. This part remains the same. The nitrile group changes to acid groups, which means again this is hydrolysis, so you need dilute acid. 5. Compound X contains the same functional groups as citric acid. So they're telling you that compound X contains an acid group and an alcohol group. The table describes some of the similarities and differences between citric acid and compound X. So citric acid has does not have a chiral center. Now this is citric acid, where this carbon is not chiral center because it has double bonds, and chiral centers do not have double bonds. This carbon atom is bonded to 2 hydrogen atoms, and chiral center is a carbon atom that is single bonded to 4 different groups of atoms. This carbon atom over here is not a chiral carbon because it is bonded to 2 same groups of atoms. This one over here and this one over here. These are the 2 same groups, CH2 and then the acid group, CO2H. And again, this carbon is bonded to 2 hydrogen atoms. This one double bonded. Also, this one is double bonded. And then the reaction of sodium with both of them causes fizzing. Now sodium reacts with alcohol and acid groups. As you can see, in citric acid you've got 3 acid groups and an alcohol group, so sodium reacts with all of them. And the reaction with the oxidizing agent can oxidize compound X, but it cannot oxidize citric acid. That's because over here acid groups cannot be oxidized. The group that can be oxidized is the alcohol group. But remember that only primary and secondary alcohols can be react. That means the alcohol group has to be on a carbon that is bonded to 1 or 2 hydrogen atoms. Now this, as you can see over here, this carbon atom is not bonded to any hydrogen atom, and so this is a tertiary alcohol, which means that it cannot be oxidized, which is why you'd observe no color change on the reaction of citric acid with oxidizing agent. A. Complete the equation to show the reaction of excess sodium with citric acid. Show the skeletal structure of the product. So again, sodium would react with the 3 acid groups and this alcohol group, which means you'd need 4 sodium atoms. And for the product, you'd have this compound. All of the hydrogen atoms are replaced by sodium, and you'd also obtain hydrogen molecules as the byproduct. B1. Use the information in the table to deduce the skeletal formula of X, C3H6O3. Draw the skeletal formula of X in the box and label the chiral center of the compound X with an asterisk. So from the table we can make out that X, as mentioned in the question, has same functional groups as citric acid, so it's got at least a single acid group and an alcohol group. Now you've got 3 oxygen atoms. That means there's only 1 alcohol group and 1 acid group, since 2 oxygen would be used up in a single acid group, and the third and the last one would be used in the alcohol group. And we also know that the alcohol group has to be primary or secondary. Now we also know that the alcohol can be primary or secondary to be able to get oxidized to form to cause the color change from orange to green. So now we can start by drawing the C3 backbone, an acid group. And then now as for the hydroxide group, if you were to place the hydroxide group on the terminal carbon atom, you'd be able to see that there is no chiral center, since this carbon is double bonded. This carbon has two same hydrogen atoms. This carbon also has two same hydrogen atoms, which means the hydroxide group has to be bonded to the second carbon atom, because the table says that compound X has a chiral center, which means you'd have CH3, the terminal methyl group, and then CH, and this carbon atom in the center is bonded to an OH group, and then the followed by the acid group, and you're supposed to be drawing the skeletal formula. Alright, so we've got 1, 2, 3 carbon atoms, and then the carboxylic acid group. You've got an alcohol group on the second carbon atom, and this is the chiral center, the carbon that is bonded to alcohol group. To explain why X, so this compound reacts with chromate ions, dichromate ions, but citric acid does not. So again, dichromate ions are oxidizing agent which can oxidize the alcohol group, but in order for alcohol groups to be oxidized, they have to be either primary or secondary alcohol. In the case of X, this is a secondary alcohol, since it's bonded to a carbon atom that is bonded to two alkyl groups and a hydrogen atom over here. However, citric acid, this is a tertiary alcohol, since the alcohol group it's bonded to a carbon atom that is not bonded to any hydrogen atoms, which makes it a tertiary. See, compound X is one of a pair of stereoisomers. Stereoisomerism occurs when a molecule has at least one of two key features. State the two key features that give rise to stereoisomerism. So the two kinds of stereoisomerism would be geometrical and optical. Geometrical isomerism occurs in alkenes, or when you've got a double bond between two carbon atoms that are bonded to two different groups of atoms. And so that's the first case. As for the second case, optical isomerism occurs due to chiral centers. That means when you've got a carbon atom that is single bonded to four different groups of atoms. The structural isomer of compound X does not fizz when added to sodium. Explain what is meant by structural isomer. So these are isomers that have the same molecular formulae but different structural formulae. And this is it. We are done with this paper. Thank you for watching.